Hello everyone, I'm Wenkai. Today my topic is improved scalability of demand-aware data center topologies with minimum route length and congestions. This is joint work with Maciej, Pacut, Klaus-T, Foerster, Stefan, Schmid. All of us come from University of Vienna, and Alexandre Labbe from ESTA Paris. Let's start. Nowadays, the data center has become a vital infrastructure of our society. We can easily observe that the traffic size grows almost exponentially over many years. In order to cope with this rapid increasing amount of traffic in data centers, we have to continuously improve their productivity. Unfortunately, the end of Moore's law in networking resulted in more equipment and a larger network for improving the capability. However, the restriction from the hardware development brings more opportunity for researchers, where improving the top rack connectivity by a better network design becomes a pressing issue. Traditional network design may be in different flavors, like a factory or CRISPR, but they are all demand oblivious, which optimize the worst case of all-to-all demands. For example, the current data center design, such as the popular factory topologies, focus on improving all-to-all throughput, but increase the bisection bandwidth. On the other hand, as soon as the traffic becomes more structured, the throughput suffers. However, studies has shown that the traffic inside the data centers is often not uniform all-to-all. In some examples, even up to 99% of the pairs exchange no traffic at all, invoking the need for design paradigm shift. As real-world communication is usually structured, demand-aware design takes the lower structured information to solve the problem with more pertinence. Here, we are particularly interested in the demand-aware network topology design on the physical layer. The general goal of demand-aware bounded degree network design is to find a network satisfy a given degree bound delta, meanwhile minimize both its average route length and the congestion for the given demands. We confront several challenges. A constant degree bound delta indicates a sparse network, which has a high diameter but low connectivity. There's a dilemma between shortest route length and low congestions. The shortest route length means the flows will converge to the shortest path, which causes a bottleneck. But low congestions require many paths between a pair of demands, which has a high degree problem and also the long route problem. The input of this problem is a degree bound delta and a demand matrix D, where each entry Dij means a communication intensity from I to j. We also define a demand weighted graph GD. For each non-zero entry Dij, there is an edge between I and j, with the weight Wij equal to the mutual communication demands. Now we come to define the congestion and the route length. Given a demand matrix D, we found a network N and a routing scheme for serving D on N. So for each pair of nodes, we use his communication distance, multiple his communication intensity, and a sum for all the pairs. This is our routed length. And to define the congestion, we found the highest load incurred by current routing scheme. This is our congestion. Now, let's formalize this ByObjective optimization problem. We are given a demand D and a degree bound delta. We try to find a network N satisfy this delta and a routing scheme such that the weighted routing length is upper bound by C of optimal route length, and the congestion is upper bounded by D of the optimal congestion. This ByObjective optimization problem has been mentioned and discussed in several previous work. We are the extension work of the paper from the DISC 2017 and the InfoCon of the 2019. We first talk about our contribution in the time complexity. When the demands graph is a general graph, before people show it's already NP hard to optimize either the route length or optimize congestion. But When the demand graph becomes trees, now we show it's also NP-hard to separately optimize routing length or congestions. Especially even we require this desired network must be a tree, it's also NP-hard. Now we introduce our approximation results. When this demand graph induced by trees, this is our approximation results. Approximation ratio 2 for routing length and 6 for congestions. Compared to previous results, although we are suffer more congestions, but we decrease this routing length substantially. That's why it still makes sense. Now we start to introduce our approximation algorithm. At first, we were only focused optimizing this route length, not congestion. We will introduce the technique called the Ego Tree. We start with a simple case where the demands D induced by a star. Actually, it means it's only one node have a communication with his children, like this. So the root S have communication for k children, but there is no communication between any two children, and their communication intensity is defined by W. In order to find an optimal network to optimize this routing length, we first construct a tree with k plus 1 nodes. Recall here we have k plus 1 nodes. And we require this tree is called a full tree, such that the root can have delta children, and the other nodes maximum can have delta minus 1 children. And we especially require that this is a full tree such that you couldn't insert nodes between these nodes anymore without violating this restriction. They only can insert nodes after this last nodes. This is a Ego tree we called. To complete the construction of the Ego tree, we still need to mapping the original nodes to this new constructing node. So we first mapping the root to this root directly. Then we sort all the children W to W apply with the long increase order respect its communication intensity. Then, according to the order of W prime, we will insert nodes from left to right and up to down, such that the highest communication intensity one should go first one. Then the second highest one go this one. Then the last one wouldn't have the communication than other people in front of him. It's easier to say by this structure we can achieve this optimal routing length, because when we construct this tree, we know we cannot insert node anymore. When we place these nodes, we use this greedy way, such that if you want to move any nodes closer to S, then there must be another node with higher communication intensity go down, such that you couldn't make your routing length decrease. Okay, so when a demand is induced by a star, we can construct an Ego tree to find the optimal network for him in polynomial type. But when a demand is become a general tree, it's not like a star anymore. How can we still find this good network for him? You know here, each of the node, either he have communication for S, and then he also have communication with someone as his children. So we cannot use the Ego tree so directly. Then, when the demands are induced by a general tree, not star anymore, we can still logically participate into different star, as we show by this kind of a colorful triangle. Each node, it can be a children of one star and the root of a different star. Then, for each of this star, we can still construct the Ego tree for him. But if we have this Ego tree for each of the nodes, we cannot merge them into a feasible solution to satisfy delta, because it already have a delta in one tree. If you merge two trees, there might be violated data. But since each Ego tree is like optimal for this star, the sum of this routing length can be used as a lower bound. In order to obtain a favorable solution by merging this ego tree, we have to change the fan out. Now we construct an ego tree with the fan out alpha and beta. So their value is here. So alpha plus beta will not more than delta. Then for this t, he is a child in this ego tree and a root in this ego tree. When we merge them, his degree is maximum alpha plus beta is no more than delta. That's why we can obtain favorable solution by merging this ego tree. Now we show our method can achieve two approximation. So for arbitrary demands star root at A, we construct two ego tree with different fan out. So by decreased fan out, of course, for arbitrary node T, its distance to A will become longer in this new ego tree, but we know this distance will at most be doubled. According to a definition of a weighted routiness, since this is at most doubled, that's why we still can achieve this two approximation. Now we talk about some drawback of the ego tree. It may increase the congestion. Recall how we construct this ego tree. Then these nodes would be has higher communication intensity to S than the other nodes in the same level, which means this edge will suffer very strong congestion. This is drawback of the ego tree. Before we talk about the congestion, let's recall a problem called a scheduling and identical machine problem. We have a set of jobs. Each of them have a duration Li. We have a set of machines. Then we need to send each job to a machine to minimize the max span. Max span is the maximum loaded machine. And what we do is like we sort J in the order of a long increasing duration. We call it J pri. Then we set J pri sequentially to machine from 1 to m. If we reach m, then we turn to 1 again. This is round robin. Then we can achieve two approximation for this max span. Now we introduced our idea of a round robin tree to improve this congestion. So for this root, we have delta children. We suppose each of the children as a machine. We have a delta machine. So for W pri, we sum them into these delta machines. If a node sum to a machine, then they will always stay on the subtree of this node. By this way, we know the congestion on these highlighted nodes will like two approximation of an optimal solution. Similarly, in order to merge this round robin tree, we have to also change the fan out. By changing fan out to alpha, then we know delta divided by alpha is smaller than 3. That's why we can achieve two approximation for the congestion. By this way, we also note the distance to S will not be changed. So we still have a two approximation for the routine length. Up to now, we assume our demands are induced by trees, but now we change it. So now assume our demands induced by sparse graph. What does sparse graph means? It means that the average degree is constant. Maybe some nodes still have a non-constant degree. By our experience, we found the Facebook traffic graph actually is sparse. So we have analyzed both database and Hadoop. We found more than 95% traffic shows a graph with average degree maximum 4. And we change this sampling time to 100 seconds. The situation still hold. That's why we think a Facebook traffic graph is sparse. When the demands are induced by sparse graph, we also improve the privacy results. To achieve near optimal routine length, our network have a maximum degree bounded by 3 multiple the average degree of the demands, but the privacy work, they need a factor of 12. This is also a significant result. So due to the time, we are not given detail here. So we are stop here now. Thank you for your listening. I welcome your questions.